Internal combustion engine design, testing, and performance. So for problem number 1, we're given with an Otto cycle which consumes 8 liters per hour of gasoline. It develops power at a rate of 25 kilowatt. So this is also our work net. SG, or specific gravity of the fuel, is 0.8. SG is our density of this fuel divided by the density of water, which is 1000 kilograms per meter cube at the standard conditions. Calorific value of the fuel, or the heating value of the fuel, or the burning power of the fuel, is 44,000 kilojoules per kilogram. So we need to solve for the indicated thermal efficiency. One assumption for this problem is that the energy produced by the fuel is also our indicated power, such that our thermal efficiency is work net divided by heat supplied, or simply output divided by input. Our output, or the power developed, is 25 kilowatt, and that is given. Heat supplied, so for the heat supplied, that is equals to the heat that is coming from the fuel, mass of the fuel times the heating value. For the mass of the fuel, we can use the relationship for density, which is mass over volume, so that the mass of the fuel is density of the fuel times the volume of the fuel. For the volume of the fuel, so it is given as 8 liters per hour. For the density of the fuel, we are given with a specific gravity. So if we multiply specific gravity with 1000, we can get the density of the fuel. That's why we have Sg times 1000 kilogram per meter cube. So our density of the fuel, and then times the volume of the fuel, and then the heating value. So our heat supplied, substituting all the values and then converting liters to meter cube and hour to second. So we have heat supplied as 78.22 kilowatt, and then substitute to our formula for thermal efficiency. So we have 31%. So our engine is 31.96% efficient in converting the energy from the fuel into indicated power, or the power developed at the combustion chamber. So sample problem number 2. So we have a diesel engine which consumes fuel, or the mass of the fuel consumed, 5.5 grams per second. The power developed, or our BP, is 75 kilowatt. The mechanical efficiency is 85%. Take note that mechanical efficiency is BP over IP, or the brake power output of the shaft divided by the indicated power input from the combustion chamber. We need to calculate the brake specific fuel consumption and the indicated specific fuel consumption if the lower heating value of the fuel is 44 megajoules per kilogram. So for the BSFC, so we can use our formula in slide number 40 of our presentation. So our BSFC is simply the amount of fuel consumed per brake power developed. So this tells us that a particular amount of power is produced when we use that particular amount of fuel in kilograms per hour. So if it is ISFC, we just have to change BP with IP. So going back to our problem, our BSFC is mass of the fuel divided by BP. Mass of the fuel is given, the fuel consumption, and then the BP is also given. So we can solve for BSFC. ISFC, we're not yet given with IP, but we can calculate using the relationship in terms of mechanical efficiency, which is also given. Rearranging that one and solving for IP, so IP is 88.235 kilowatt. And finally, our ISFC is mass of the fuel divided by IP. So our IP is 0.06233 grams per kilowatt seconds. So for sample problem number 3, we are given with a 6-cylinder gasoline engine which is operating at a 4-stroke cycle. The bore of each cylinder is 80 mm and then the stroke is 100 mm. Clearance volume is 70 cc. The speed is 4,100 rpm. the mass of the fuel consumed is 5.5 grams per second, and the torque is 160 Newton per meter. The calorific value of the fuel is 44,000 kilojoules per kilogram. So we will calculate for the BP. So the brake power, going back to slide number 29, can be calculated using this formula. Brake power is just 2 pi NT. Take note, 60 is just a conversion factor from minutes in RPM to seconds. So that our brake power is 2 pi N, which is 4,100. We convert minute to second, and then torque. And then we convert Newton to kilonewton so that our unit is kilowatt. So BP is 68.69 kilowatt. For the mean effective pressure brake, so the mean effective pressure brake can be calculated using the formula for mean effective pressure. So mean effective pressure is the hypothetical or the average pressure that is assumed to be acting on the piston throughout the power stroke. The PMB can be calculated by using BP instead of IP. And for this formula, 60 again is just a conversion factor. And then we have L, the stroke, A, the area, the cross-sectional area of the cylinder, N is the speed. So for 4-stroke cycle, when you use this formula, you divide N with 2. But if it is a 2-stroke cycle, you no longer have to divide it by 2. The reason is, for a 4-stroke cycle, for a complete cycle will be 2 revolutions. Whereas for 2-stroke cycle, a complete cycle for 2-stroke. So K is the number of cylinder. So going back to our problem, so we can solve for the PMB by using BP instead of IP. So substituting all the given, so when you use this formula, your BP should be in kilowatts so that your result is kPa. When you use watt, your result is Pascal. Then L should be in meter, and then the area should be in meter squared. That's the area of the cylinder. We're given with the cross-sectional area from the stroke, from the bore, which is 80 mm. And then N we divide it by 2 times 6, which is the number of cylinder, 6 cylinder. So we have 666 kPa. We convert kPa to bar by dividing it by 100, because the conversion is we have 100 kPa per 1 bar. So PMB is 6.66 bar. So for the third requirement, which is the brake thermal efficiency, the brake thermal efficiency is the thermal efficiency based on brake. So we will use brake. So brake divided by brake as our output, and then the energy from the fuel as our input, times 100%. Brake is already solved. So for the mass of the fuel, we should convert grams to kilograms so that our mass is consistent with the unit also of the heating value, which is per kilogram. So our brake thermal efficiency is 28.34%. And finally, for the relative efficiency is telling us how efficient this system is as compared to the ideal. So the ideal is the maximum for this purpose. So the ideal for this problem is assumed to be a constant volume cycle. So recalling our previous discussions, constant volume cycle is an Otto cycle, which is SVSV. The V there means constant volume. K is 1.4. And we know from that lesson that the Otto cycle efficiency is given in terms of the compression ratio. Compression ratio R can be calculated through the ratio of the total volume to the clearance volume. Total volume is the swept volume plus the clearance volume. Clearance volume is already given, so we need to solve for the swept volume. The swept volume is simply the volume of the cylinder, which is pi r squared times length, or pi over 4 d squared times length. So substituting, so we can solve for the swept volume, and then putting all the value to our formula for R, we can get R as 8.18. So the Otto cycle efficiency is 56.859. So K is 1.4 that it is given. So finally, our relative efficiency is Substituting to our formula is 49.91%.